All right, I think this is the time to start. Great pleasure for me to have Igor Pak here on our seminar to introduce him. Igor Pak is from University of California at Los Angeles, and he will speak about integer points in polytopes. Please.
Thank you. So I'm gonna talk about some old results that we proved with Danny, and some later results that we proved after our older work, but somehow because of the whole pandemic, I was unable to talk about any of them. So just about everything I'm going to say that's relatively new is joined with Danny, and I'll talk about integer points and polytopes. So here we go. Let me define polytopes. So convex polytope is going to be defined over Z, and by that I mean we're going to think of even though a polytope is a geometric object which sits in RD, it's going to be defined by matrix A and an integer matrix A and an integer vector B as using inequalities AX less or equal to B. And I'm gonna ask you all to show thumbs up if you're following me. I'm going to be asking for that, and show thumbs down if I can see you, or there is a crying emoji just to tell me if you can't understand what I'm saying, or there's something that you want me to explain, and I'll do that. So let's try this. Is everyone clear about the instructions? Yeah, I don't see many thumbs up. So those of you who are not on video should be able to learn the emoji buttons somewhere on the bottom. Oh yes, I can see you. Some of you already figured it out. Okay, good. So I'm assuming there are no questions about what's a convex polytope, and so I'm gonna move forward. Now I'm gonna define integer points in a polytope as you would think they are. It's an intersection set of integer points, an intersection of the polytope and ZD. So there are two problems that I want to talk about: the decision problem and the counting problem. They're essentially similar problems. The first problem asks, does there exist an integer point in ZD? And the second problem asks, given a polytope, compute the number of integer points in ZD. That's what the talk is going to be about. Everyone okay with this? Everyone clear? Oh yeah, so you should learn emoji. Yes, good. So if you don't follow me, just to figure out there has to be crying emoji somewhere. Now I want to start with some background, a very general background, which I want to somehow connect to the story. So the first problem is about knapsack. Given integers a1 up to n and an integer m, I want to know if there exists a subset of integers which adds up to m. So that's a knapsack problem, and as stated, you can immediately see that this problem asks about number of integer points in a certain polytope, and classically knapsack isn't B-complete, and number of solutions to the knapsack is sharply complete. And as a corollary, we conclude that when the dimension is unbounded, both decision and counting problem are very hard. So from this point on, we're going to be working with bounded dimension. Are there any questions about knapsack? Everyone good for me to proceed? Yeah, okay, good. Good, I can see your thumbs up. Okay, excellent. So before I move on, I want to talk about three partition problem, which is a very similar problem. Given a set of integers a1 up to 3n, note there is a 3 here. We're going to, and suppose these numbers add up to 3 times an integer. The question is, does there exist a 0, 1 matrix? It's sort of easier to think about it in this way. Let me just say it in colloquial terms. What you want to do is you want to split the 3n numbers into n triples. You want to split them into n triples, all of which add up to the same number m. Okay, I think I.
Are these numbers integer or not?
Everything is an integer.
Okay.
Everything is an integer, and this is n times m. And so this is really a question about finding a 0, 1 matrix, which sort of looks like that. So that we have, in addition, the following set of equations, which are the ones that I told you when you split into n triples, so that sum in every triple is the same number m. Okay, everyone clear about the statement? Yeah, the statement of the problem. It's somewhat less common, I think, than knapsack, and but it's still classical. So the three partition is, I'm going to say what I mean by this, is strongly NP complete, and the number of solution to three partition is strongly Sharp complete. Let me explain what I mean by that. What I mean is those integers that I have, a1 up to 3m, I'm going to think of them as given in unary rather than in binary. Okay. So strongly NP complete means that it's NP complete in unary. Strongly Sharp complete means that it's Sharp complete in unary. Okay. So what this is, and obviously this is again number of integer points in a convex polytope. So what this is saying is the problem is somehow even harder than you would think it is. So it's hard even if in unbounded dimension, even if the numbers that you that the numbers in the input you have are very, very small. Everyone clear about this? Yeah, can I move on? Okay. Okay, good. So, so as I said, new results are going to concern bounded dimension. But before I get there, let me mention a couple of open problems, and one of them is sort of my favorite. This is a graph counting problem. Suppose you have a sequence d1 up to dn. The question is, so let me see. So 0 less or equal than di less or equal than n, I suppose, and the question is, find the number of simple graph of on n vertices with degree sequence d. Okay, that's the question that you want to say, and it is completely obvious how to state it in terms of number of integer points in polytopes. You can sort of think of this symmetric n by n matrix, and Mij sort of encodes whether you have an age or not, and if you do that, then you conclude that this is again one of those problems that you've seen before, problem whether of counting number of integer points in a polytope, and suddenly turns out that we don't know if computing number of graphs with given degree sequences is actually Sharp complete. That's an open problem. Is the problem clear? Yeah.
And what about the decision problem?
Oh, the decision problem is easy. That's actually coming here. I'm going to leave it as an exercise. Deciding if there exists a graph with given degree sequences, that's very easy. And I think I teach it occasionally when I teach graph theory. So I'll leave it as an exercise. And so let me say in the first note, and this is such a well-known problem. There are just numerous asymptotic formulas for various ranges of degrees of the graph. There are numerous approximating algorithms for the number using, there is a sort of simple to define Markov chain when you can switch two parallel edges to sort of for them to cross. When you do that, that keeps all the degrees, but somehow one can easily show that the underlying graph is connected. You can run a Markov chain, and the question is, does the Markov chain convert mixes in polynomial time? And often it does, and there is just a gigantic amount of literature on that. So those of you who want to know more about this, Nick Wormelt gave a talk at the ICM in Rio, where he spent the whole talk talking about basically many different aspects of this problem. Okay, can I move on? Any questions, or is there any questions about this? I'm assuming thumbs up is meaning I can move on. Everyone good? Okay. I want to mention my personal favorite problem. This is a problem which is closely related to the previous one. It's about the number of contingency tables. So contingency tables are integer matrices. So everything inside the xij is greater or equal to 0, and rows add up to ai's and column add up to bj's. So you're given two vectors, a1 up to am and b1 up to bm, and you want to know how many how many matrices are there with given row sums and column sums. Again, the decision problem is completely trivial. I'll let you figure it out. Well, maybe I can just tell you the answer. What you need is a1 up to am equal to b1 up to bm. That's all you need for the decision problem to say yes. Okay. Everyone clear about this?
And if there are some restrictions from above on xij?
No, no. The xij, you know that they have to add up to here. So if there were restrictions, that would be harder problem. So for example, if xij was 0, 1, that would be similar to the counting graphs. In this case, this is sort of like counting multigraphs, of bipartite multigraphs. Everyone clear about number of contingency tables? And again, in this case, it is a conjecture that the number of contingency tables is strongly Sharpe complete. We don't know that, and we're not particularly close. And let me mention a similar note to the one I said before. Approximating the number of contingency tables is a major open problem. It's especially important in statistics, and there are many results known about this all. There's so many. If I start talking about that, I'm never going to finish this talk. That's it. That's all I have to say about contingency tables. Well, before I move on, let me mention that it is also conjecture that there exists a plus which for the number of contingency tables. So what we're conjecturing is that there exists a polynomial time to approximate the number of contingency tables within 1 plus or minus epsilon. We don't know that either. And before I finally move on, let me also mention why this is important for things. That's another thing I care about, an algebraic combinatorics. there are bounds on important numbers in algebraic combinatorics in terms of the number of contingency tables. So, for example, Koska numbers are bounded from above by the usual contingency tables, and similarly, Kronecker coefficients are bounded from above by the number of three-dimensional contingency tables, with sort of two-dimensional sums being lambda i's, mu i's, and nu i's. That's our recent result with Greta Panova. I don't mean for you to explain what are these Kronecker coefficient and Koska numbers, but somehow the point is any upper bound that one would have for the number of contingency tables gives an important application in algebraic combinatorics for things we care about. Can I move on? Yeah. If I can, ask me questions. This is a good time to ask a question. Can I move on? Okay. So I'm never coming back to this, but because from this point on, I'm going to talk about complexity results, and I'm not going to prove too much, and I don't mean to, or prove anything, but I'm going to try to service some very well-known results and some of our recent results, what happens when dimension is fixed. So from this point on, D is fixed. Okay. So I'm going to start with a foundational result by Lenstra, which says the following. He's basically saying, so whatever is underlined with red is the number of integer points in a convex polytope, as we discussed before. So now A is an integer matrix and B is an integer vector. Only D is fixed. M doesn't have to be fixed. And the problem is this is what's called integer programming in bounded dimension, and it can be solved in polynomial time. Is everyone okay with this? I'm gonna show a picture in a minute, but any questions about this?
I wanted to ask a question. So here, P with respect to M growing, or with respect to the numbers in matrix A growing, or both?
No. So
the total size of input.
The total size of the input is the sum of the bit lengths of numbers in this matrix. So you should think of this matrix as encoding the whole input, and the input can be large.
Okay, so we allow both, like it both the dimension kind of and both the large numbers. So okay.
Yeah. Okay. So somehow the result is very, very strong. It works in binary. It works when M is not fixed. You see what I mean?
Yeah.
Okay. Any questions? Any other questions about this? Okay. So let me before I sort of give a small picture, let me immediately mention the second key result in the field. This is a theorem due to Ravikkanen, who basically says we can in fact add one more quantifier. So this is from this point there exists x so that ax less or equal to b is still the same, but now we can also do for all y. And bear with me, I'm going to explain what I mean by that. What he's saying is when all the dimensions L and G are fixed, this M still does not have to be fixed. This problem is still in P. This is a decision problem whether for Ly there exists X so that there exists a solution. Now, before I sort of move on, let me explain what's going on and what are the issues. The first problem is a rather simple looking problem, we're asking that, whether there are integer points in a polytope. So everyone should be clear what that means. However, the second problem is a little funny. What we're doing is we're looking at integer points in this polytope, and we're asking, is it true that for all points which lie in some polytope in the projection, there exists one integer point in the polytope above, which is defined by ax less than b, which projects onto that integer points in the projection. So it is a tricky kind of problem. Do you see what I mean? And the reason it's tricky is basically because the projection of integer points in a convex polytope does not have to be an integer set of integer points in the projection of the polytope. This may seem a little funny because naturally you would, if this was over reals, that would be obviously true. However, if you sort of think of this interval and you project it down on this line, you're not, it's a little maybe hard to see, but you're not going to get every integer point in the projection. You're going to get every other point in the projection. So smaller points that sort of points here are not actually covered when you do the projection of this line slanted by y equal to x over 2. Do you see what I mean? So because of that, figuring out if for all points in some polytope on the bottom there exists one integer point in the big polytope above, that becomes a much harder problem. That's what is the issue in this whole problem, and Ravikant figured it out. Okay, can I move on? Yeah. I'm going to wait for a couple more thumbs up. Okay, Janos. Oh, Janos also saying thumbs up. Okay, maybe you knew this. Okay, so enough with the decision problem. I'm going to say similar results for the counting problem. And there are, just like there were two results I showed you for the number of IP solutions, integer programming solutions, Barvinek showed that you can compute it in polynomial time. In the same way, some 10 years later, Barvinek and his former student Woods showed that for fixed dimension, the number of this solutions, this PIP stands for parametric integer programming, number of PIP solutions can also be obtained in polynomial time. So let me remind you what they are. So IP is so Barvinek was able to make counting version of Lenstra result, and Barvinek Woods later were able to make a counting version of this Cannon's result. Everyone clear about this? The statements? Yeah. Okay, and I'm not gonna say what exactly they're doing, but somehow they're combining tools in previous results by Lenstra and Cannon with the idea of counting of using generating function, and that's the following idea. So essentially, what you want to do instead of counting, turns out that it's best to take a generating function for the set of points which lie in your convex polytope. Later, you can substitute variables to be one, and you're good. This is not super obvious how to do that, but somehow the degeneracy problem can be managed. And now, how do you calculate the number of integer points in a convex polytope? What you do is you sort of write your convex polytope as an alternating sum of cones. The cones will have to be simple, but in the plane, everything is easy to make simple. And the idea is that you sort of, you take a big cone like that, you subtract another big cone like that, and what you have left is a smaller cone. And there are problems with low dimension, so you have to add and subtract something of low dimension. And at the end, you get some kind of easy to handle rational function. That's what Barvinek introduced. I mean, that's Brion and Vern's approach to the problem. And Barvinek was able to combine Lenstra approach to get the counting results for the number of integer problem, number of solutions to integer problem. Is everything okay? Everything clear about this? I'm gonna wait. I'm never coming back to this. So okay. I see some thumbs up. Okay. Good. So now let me sort of tell you our older results, and I'm not never going to tell you the full versions because they're all becoming kind of technical. However, some smaller versions are easy to understand, and that's what I'm going to do. So what we look is at the following problem. This is this problem over here. So there exists basically z, y, and x. X is 6-dimensional, y is 2-dimensional, and z is 1-dimensional. So that the number of solutions in the number of integer points in this convex polytope defined by a x, y, z less or equal to b is actually NP complete. Now that should be mildly surprising. So let me now tell you why. Now the whole matrix here has finite size. So we're talking about in total 214 numbers that are in the input. 24 times 9 plus 24. You see what I mean? So we have in total 240 numbers, and somehow the problem is the whole NP completeness is sitting in these numbers. That's very, very different from the usual type of problem about 3 colorings or Hamiltonian cycle. This is a different kind of example of NP completeness. And for years, people conjectured that this is impossible, that all these problems can be solved in polynomial time. So that's what we did in 2017 in our Fox paper. Is the statement clear? Yeah. Okay. So the second, our second result is very similar to the first one, but now we actually can drop the dimension. This is dimension 3, 2, and 1. There's just not the whole. We again have only 3 quantifiers, and the whole number of variables is 6, the total dimension. And however, for technical reason, we have to have a rather large, set of inequalities that has to do with the upper bound theorem. Essentially, because we construct our polytope using vertices, not using facets. So if we want to understand the number of facets, we just plug it into the upper bound lemma. Everyone clear about this? So these are 2 kind of sister results that we proved, which shows that there is no way to sort of keep polynomiality in when you add quantifiers. The Lenstra theorem and the Cannon theorem is all that you get. You don't get to have 3 quantifiers and still being polynomial. Everyone okay with this?
I maybe have one question about what happens if we flip the quantifier. So for every there exists such that for every.
Yeah, then it's going to be co-NP complete. And that's what I mean by special cases. If you have k quantifiers It's either sigma k minus 2 or pi k minus 2, whichever it is, depending on the last quantifier.
Okay.
Okay, and there is more to the story which I'm not telling you. Any other questions? So let me give you some, 2-minute hint of what do we do. What we do is, this is just, what I'm giving you is 2 ingredients of how to construct this. The first, first, what problem do I reduce it to? So we reduce it to an AP cover problem. AP stands for an arithmetic progression. So here are my arithmetic progressions. The arithmetic progression is exactly what you think they are. They start at the number AI, and then they go, so they're AI, AI plus BI, AI plus 2BI, and so forth. So that's my arithmetic progression AI. And the question is there a point on some interval which is not covered by arithmetic progression? Now, that's one of the classical problems. You can find it in Gary Johnson's book. So that problem is NP-complete, but to no surprise of anyone. So let's just, for the sanity check, to understand that if there exists a point that's not covered, if somebody gives you a point and say that point is not covered by arithmetic progression, it's easy to check that it's not covered by just trying just checking all those numbers to see that each AI does not cover X. Everyone clear about this? So checking whether all arithmetic progression covers the interval is in coin P. Checking whether there exists a point that's not there is in NP. And that problem turns out to be NP complete. Everyone clear? Questions about AP?
So maybe one thing to add is that it's in the number of bits, right? So all of this, yeah, we should think of, because maybe for some people it's not typical.
That's correct. So everything here is in binary.
And actually checking that it's this verification that you mentioned is not as easy as it may seem immediately. I mean, it's easy, but
it's called
using power.
It's
a simple exercise, but it's not completely straightforward, okay, because it's
it's simple enough. So let me, before I move to the second idea, let me mention how did this come up before. You see, when you do this projection, you get some kind of arithmetic projection, arithmetic progression on the bottom. That's always what happens. That's where that's why arithmetic progressions are actually highly relevant to this, because essentially what you want to think about is every polytope is some kind of alternating sum of high-dimensional arithmetic progressions. And as if numbers are very, very large, number of arithmetic progression doesn't really depend on somehow. It depends only on the combinatorial structure of the polytope, but not on the numbers themselves. So the second idea is, what do I do now with arithmetic progression? Turns out that I can embed this arithmetic progression into all of them, can embed into one giant polytope, which will be later projected onto something where these arithmetic progressions become evident. So in fact, if you take some alpha, so alpha is a rational number, and look at a set of points below the line, there are arithmetic progression that you see on the edges of the polygon below the line. This is something that should be familiar to many of you. Those who it's especially nice when alpha is a golden ratio or something like that. In that case, arithmetic progressions disappear; it all becomes one. But in general, you get you can get large arithmetic progressions, and somehow this number alpha is the only number that at the end is going to be very big. All other numbers in this matrices A, in those matrices A, are going to be relatively small. It's at the end of the day, it sounds like there are 240 numbers, but in reality, only one of them is going to be huge. Everything else is going to be small and nice. So at the end of the day, the whole complexity, computational complexity, which goes into proving NP completeness, is really pushed into one number alpha. That's how the proof goes. I hope I didn't confuse everyone completely. So, any questions about any of this? Because from this point on, I'm just going to continue bragging about our results, and I'm not going to explain too much. So if you want to get some beef, this is the place. Okay. So can I move on? Let's try again. I want to see you. I want to see you try. Okay, good. So now I want to mention a couple of applications to counting. And the first application is both theorems 1 and 2 that I showed on the previous slide actually going to have counting versions. So whatever I say, if instead of decision problems that I'm giving here, if I'm asking how many solutions to this, that's gonna be Sharp P complete. That's all. That's an application to counting, and that's my first application. So my second application has to do with counting projections. Everyone clear about this? The first application? Yeah. Any questions here? Okay. Okay, good. So now I'm gonna here is the definition. I'm gonna look at a set S, and I'm gonna define pi of S to be number of points, integer points in the projection, which are projections of integer points in my set. So in this picture, my set S is here, and I'm gonna looking at points. I'm gonna take all integer points in my set S, and I'm gonna project them down, and I'm gonna be counting number of integer points in the projection. Is the statement clear? So note that this is a very strange counting, because, for example, it's counting this point once, but it's counting. So this point is counted once, and this point is counted once, even though in the fiber one has one point in the pre-image and one has 2 points. You see what I mean? So this has nothing to do with number of integer points inside S. This is really a different kind of counting. And now what we prove is a rather strange result. What we prove is that if you in R3, if you have 2 convex polytopes, computing this number pi in the difference of 2 polytopes is actually Sharp P complete. So to give you an idea what's going on, so here is one polytope, here is another polytope. Oh, let me draw it with another color. Here is another polytope. What you're looking at integer points in the shaded region, and you're projecting them down here on this axis. And you count, so you're projecting integer points here, and you're counting which points in the projections do you get. And but because this is Q, this is Q, this is P, because Q minus P is actually not convex, this number is not particularly nice. and turns out that that's already sharp P complete. Is everyone clear about this?
And what about other operations you can do on two sets, like union, symmetric difference?
So symmetric difference works the same way as the difference, and the union works out. But however, so this is going to be my corollary later. So if you take a union of many things, it doesn't. So it sort of depends on union, how many polytopes do you take. So I'm writing this as a corollary simply because if you take two polytopes, take a difference, you can triangulate the difference. So if you can compute number of points in the projection, the union of those tetrahedrons that you get, you can that's in a special case computing integer points in the projection of q of this q minus p.
But for two polytopes, I didn't understand. It's unclear.
For polytopes, you can do it.
So it's in okay.
Yeah, in sharp, it's in FP, and that's due to Barwinek and Woods also. So pi, let me do it like this: pi of P union Q number is in FP, which means that it can be computed in polynomial time, and this is Barwinek Woods. I think they say it explicitly. So the point is, if you have many polytopes, then it's not. And actually, Barwinek and Woods conjecture that you could. So Sasha Barwinek was very unhappy when we proved all these results. Everyone okay with this? Can I move on?
Polytopes represented with the system of equations?
Yeah.
Well, with metrics?
Exactly the same way as before. I just didn't want to write this down.
Okay.
P are given by AX less than B. It's just the dimension here is just 3. So it's so remarkable that you can do a hard result in a dimension we live in. Just for comparison, in dimension 2, there is a Pix formula. You can just compute everything in trivially. There are no issues whatsoever in two-dimensional projections or anything like that. So these results are tight. Any other questions? Okay. If there are no other questions, I'm going to move to an extremely remarkable result, which I'm going to mention. So the question I'm going to ask is, how far does this go? Can we prove both generalized positive result and negative results, and somehow understand what's really going on? Why do we have this discrepancy? So one result that's I want to mention is due to Khachiyan and Porkolab is the following. It's again in dimension D, but now, so this theorem looks almost exactly like Lenz's theorem, except for a couple of bars here. So the bars, so one should look into this line, and you see that this now the matrix and the vector are defined for not over rationals, but over all algebraic numbers. So note that we still have ZD here. That's very important. We're still looking for integer solutions, but now the polytope can have inequalities with some algebraic irrationals. But as long as the dimension is fixed, so you can have equation like square root of 3 times x1 minus some cubic root of 17 times x2 plus dot dot dot. You can have complicated system of inequalities. It doesn't matter. What Hachian and Porkolab explain is that it's actually one can actually prove this using somewhat similar ideas to Lenstra and yeah, a little more. Somehow, well, I can explain more, but let me move on. Is the theorem clear? Everyone okay with this theorem? I'm going to wait for a few more thumbs up, because that's a difficult theorem. It's difficult both to understand and think about how can that be. Another, in a different direction, I want to start with a really old result by Pressburger, who basically proved the following result. I'm writing it slightly colloquially, but you'll understand what I mean. So if you have any finite sequence of quantifiers, and the Boolean formula here involves some kind of inequalities. So the inequalities can be of the kind x1 minus 3x7 less or equal than 19 or something. So everything is over integers here. However, you can have not just inequalities, you can have a Boolean combination of inequality. You can say this has to be true, or that has to be true, or neither of those has to be true, but something else is true, and so forth. Is this clear what I mean? So for any finitely many quantifiers, so this is finite, and doesn't matter what it is, for any Boolean formula, you can decide whether there exists a solution or not. You can so it sort of gives a terrible bound on complexity. Decidable. This was worked out later that this has triply exponential complexity, but it doesn't. That's not super important for us now. So the lower bound is doubly exponential. The point is, this is a decidable theory. Everyone okay with this? Yeah. So we're gonna look for, yeah, okay. So I'm gonna, you should basically know this result. If you don't figure it out, it's pretty important. So recently, just a couple of years ago, Philip Hieronymi proved the following extension of this result. And it's an extension somewhat similar in spirit to Hachian and Porkolab. And so what he's saying is we don't have to stick with integers. We can have everything to be we can have everything to sit in our oh, there's a little bit of an issue. Oh, I cannot do that. Okay. So my xi's are sitting are integers. However, my inequalities are defined over the field which is obtained by adding some quadratic irrational. So you keep you take one quadratic irrational, you add to your field of rationals. Okay? Then that gives an extension of Pressburger's result. That's a kind of amazing thing to have. You wouldn't think that Pressburger can be extended in such a simple way, but it can. Is the statement clear? This is not an easy theorem. Pressburger's theorem is basically people who study standard graduate courses in logic cover Pressburger's theorem. This is dozens of pages. Everyone okay with this? Yeah, can I move on? I'm gonna wait for more. Yeah, okay. I see more people saying doing this. Okay. So so here is what we proved. What we proved is that, again, in this case, when everything is quadratic, we can get an upper bound on the decision, and this upper bound is fairly horrible. I don't know if you can how well you can see it on the screen, but it's a tower of twos of length r. Okay. Now remember, for the Pressburger, it's just a the tower was of length 3. Here, here we cannot get such a small timing, but we know that we can get into the in the tower of length r, where r is the number of quantifiers. Is this clear? Yeah. And so now m and c, the constant here depend only on my quadratic rational alpha, and nothing else. So there are really two parameters here, r and alpha. That's all there is. And before you ask me, is how tight is that? The answer is pretty tight. So we do know that that you need the lower bound is a tower. It's basically it's written the same way. It's a tower of length r minus 3. Okay. Now tau, r minus 3 doesn't seem much different from r. Of course, tower of length r is substantially larger, as you can imagine. But what's a few numbers in the length of the tower? It's not that so bad. Is everyone clear about this? Okay. So I want to mention that somehow the proof, not only the proof is long, in order to understand the proof, somehow you need to understand both Philip Hieronymus technology and our technology. So the proof is a combination of both his tools and our tools. There is just nothing nice about it at all. But that's what we get in this case for both lower and upper bound. Now, let me do the negative result, because a natural question would ask would be the following: Hachiyan and Porkolab, as you remember, did not make any distinction between. So if where was that? There was no distinction here, quadratic or non-quadratic. So why is there a distinction here? Turns out that when you have a non-quadratic irrational, the problem becomes undecidable. So this star is this star over here. Okay, so you remember that's kind of like a Pressburger fragment, and turns out that the Pressburger fragment is undecidable when you have you have coefficient in your matrix to be non-quadratic irrational. So, for example, if you take cubic root of 2 as to include it in your inequalities, then suddenly there is no upper bound on the time. Is this clear? That's a result. It's sort of Philip Hieronymus and Tikhanevich proved when Hieronymus was in graduate school. That's his dissertation. So, so what we try to do is to understand. All right. So, so now we can see where Pressburger breaks down. can we make it less complicated? So you see here, it doesn't say how many quantifiers do we need. He just doesn't say, they don't say, Hieronymi and Tikhanevich don't say anything at all. Now, what we say is, essentially, the way to read the sentence is 4 quantifiers is enough. Not only 4 quantifiers is enough, there is a really large constant, but still we computed that 20,000. So 4 quantifiers, so the whole thing is a finite fragment. So what we're saying is that wait, somehow I didn't write the conclusion. Then is undecidable. Sorry. So the conclusion is the same, but now, so what we're saying is that only 4 quantifiers is enough for the whole problem. And in fact, the total dimensions of the space where everything is going to be undecidable is finite. So everything is essentially sit 4 times 20,000. Everything is sitting in the 80,000 dimensional space, and now for any constant, could be cubic root of 2, could be anything. If you have, if you're counting the number of points in sort of projections on these polytopes and intersection, projection and intersection, then this number is undecidable. We embedded this funny Pressburger fragment in finite dimensional Pressburger, well, not Pressburger, but Pressburger with this multiplication by alpha into something that's undecidable. That's our result. No, this is
and a small question. N here is also fixed, or N has to grow here? This where B lives in.
N is not fixed. We don't know what N is.
Okay.
It's N would actually depend on alpha. It's complicated. It depends on alpha in such a complicated way I wouldn't even begin to describe it.
Okay, but for every alpha it is fixed, or?
I think so.
Okay, great.
And in fact, we did work it out. I was so unhappy exactly about the problem you're asking that I sort of sat down with my co-authors and we figured out it's not the same as in the previous theorem, but it is similar enough. So take a quadratic irrational. What we're saying is that if you have, this is 6, 4, and 11. If you have 3 quantifiers, 6, 4, and 11, then the problem, this decision problem is p-space hard. Where M is rather large. This M is given here. M is 1,000,000. I mean, our calculation give a little smaller, but roughly 1,000,000. So note that number of compared to the previous result. Where was that? Let me see. Compared to the previous result, there are at least 4 quantifiers here, and we're saying that suppose you have 3 quantifiers, then it's p-space hard. In reality, it could be much harder than that. But that's all we can prove. Everyone clear about this? Any questions? Okay. So I'm gonna finally tell you a problem that's gonna be a little bit different, and a lot of fun. So this is called the polytope translation problem, and it's sort of written in a complicated way, but in reality, it's the following problem. So we have some kind of convex polytope P, and we have a grid. The question is, what translation of the polytope minimizes the number of integer points in the P and this translated grid? Is the idea clear? So the way it's written, v times lambda. So we take a vector which is a fixed vector, and we look at various translations of the polytope by this fixed vector. You can always think of this vector to be just some kind of unit vector in the direction of x-axis. And the question is, can you minimize the number of integer points in the intersection? That doesn't sound too hard, and it's not, except it's computationally hard. So what Eisenbrandt and Hane proved that this polytope translation problem is NP hard for rational n-gons. Now think about it. What does that even mean? What they're saying is that if you have an n-gon Q, you're trying to translate a grid, and somehow, even for a polygon, you don't know how to minimize number of integer points when you do. It's kind of counterintuitive. You see what I mean? And of course, this has to do with the fact that the way I drew the polytope is not particularly enlightening. The polytope that they consider are sort of this kind of wedge polytopes where you have very thin angle between adjacent edges, which is where the whole complexity goes.
And here it's really just a translation and one fixed directional way.
Yeah,
so
yeah, it's just translation by vector. What is this? 1, 0. So you can think of V as just being 1, 0.
Is minimizing and maximizing is the same problem here?
Yes, I think so.
And where is lambda in the theorem?
If I forgot it last time, so is that okay now?
Better.
So basically, you are translating by a real number to the right, and the question is, which translation would make it the smallest?
And maybe a similar question about this Eisenbrandt-Hane theorem. So here you need n to grow.
Yes.
Okay.
It's gonna be pretty important on the next slide. So here is what we proved once we learned about this Eisenbrandt-Hane from Eisenbrandt. We were able to use our tools to show that in R4 there exists a polytope with finitely many facets, with boundedly many facets. So in R4, you actually don't need n to grow, so to speak, the number of faces. It's kind of like a trade-off. You make dimension larger, but sudden to sacrifice. I mean, you want to have finitely many facets, but you sacrifice by getting dimension larger. And the number of facets becomes very large within calculator. It's easy to calculate. Everyone clear about this? Yeah, I want to see some more thumbs up. Okay. Good. So, so now let me tell you exactly the open problem. Okay, Janusz. Let me tell you exactly the open problem that sort of what you asked. The open problem is the following. Is it true that the problem is actually hard for simplices? It might be hard for, it might be NP hard for simplices in R3 for all we know. We don't know that. And moreover, so I personally don't think it's going to be hard for triangles in the plane. So it's kind of hard to imagine that for triangles in the plane, you can, this problem would be hard, but who knows? So instead of asking for NP hard, I'm asking for integer factoring hard. I have a reason to believe there is integer factoring inside. I don't think you can do it in polynomial time, but you know, who knows? This is a conjecture. So the second conjecture is the following. Basically find the version of Eisenbrand-Hannes theorem or our generalization, if you like, just for triangles. That should be something that essentially any student who knows definitions can try to do. There's no theory here. There's just nothing here. It's a difficult problem. Difficult problem open for years. So the Eisenbrand-Hannes result is in 1912. I mean, 2012. Everyone clear about this? I have one more slide to go and I'm going to be done soon.
I wanted to ask one thing. So from your result, does it follow that in like dimension 63 there is a simplex that that is also no? So,
no,
so it's different. Okay. So we don't know it in any dimension, any fixed any dimension.
We don't.
Okay.
I personally think dimension 3 is the one where everything breaks down, but that's just my conjecture.
Okay.
Even in dimension 1000, we don't know. Any other questions? Okay. Well, last slide. So what some people do is they instead of looking at linear programming, they do polynomial optimization. And so suppose there is some kind of some kind of h is going to be polynomial, quadratic integer polynomial. So suppose you want to optimize this polynomial, and what you do is you write the usual kind of problem. You mean max of this quadratic polynomial, and you're asking about, so J is an interval actually, W is some kind of polytope, so W is some kind of convex polytope. In R5, and we're asking to solve this min-max problem, and turns out that this min-max problem is NP-hard, even though again Z is just an interval, so J is some kind of interval, and W is a polytope, convex polytope in R5. And yet this, you can get this polytope to have only 18 facets. You don't need that many facets, and the whole problem is going to be NP-hard. So this is sort of similar and sort of different to many results that you would know. Let me instead of writing, let me just mention that Matyasiewicz's theorem about Diophantine equations undecided shows so that everything is undecidable for when you have a polynomial of degree 4. So degree 4, everything is terrible. However, for quadratics, things are pretty good. So, for example, if you have a convex polygon and somehow H is quadratic, then you can solve the optimization problem over integer points. So again, we're doing integer points in this polytope polygon, in this case in polynomial time. But but the boundary is unclear somehow. And what we can show is that for polytopes which are relatively small, relatively nice, the min-max problem is terrible already. That's my final result. And in case you're going to look at this, the min-max problems is called bi-level optimization. And there's in optimization, there's a gigantic amount of literature just on this kind of problem. So that's it. That's it for my talk. I'm gonna say thank you and ask for questions. Thank you, everybody.
Thank you very much.
Thanks a lot.
Are there any questions?
Dear Professor, can I ask a question? First of all, thank you very much for a very interesting talk. I actually have two remarks. First remark is about Hachian-Porkulap result. It's, you know, Daniel Dadush, I think.
Yes.
His result actually is more general than the Hachian-Porkulap result. Actually, he proved that if you can specify shallow cut oracle, yeah, then actually the problem is polynomial solvable. And in the paper of Hachian-Porkulap, they are also mentioned that they could implement a shallow cut. So probably the result of Daniel Dadush is more general in this case. In his result, actually, all that you need is shallow cut oracle, I think. Yeah. Maybe I'm mistaken, but when I work with this paper and work of Dadush, I think it's correct statement. And second thing, there is some modern topic in integer programming called delta modular integer programming, and the Friedrich Eisenbrand and other colleagues, they proved that actually if you have, say, simplex or multi-dimensional knapsack with finite fixed number of constraints and the bounded subdeterminants in absolute value of the constraint matrix, then problem X is actually in P. It's polynomial solvable. And recently, I work with problem of counting integer points in such a polytopes with like a simplices or polyhedrons that are close to simplices and they are delta modular. And actually, the counting problem is also in P for this polytopes. And result is not very hard to prove and actually use the same ideas as in the classical Barwinic work. So maybe it can be interesting, or maybe you know something, some another cases. So I mean, there the dimension can grow. So there is polynomial on dimension. So dimension not need to be fixed. We fix actually the number of constraints. So it's like a simplex and fix the subdeterminants of the matrix.
Okay. I mean, as I said in the beginning, in the lecture and Canon, number of constraints is actually not fixed. It's the dimension that's fixed.
In this result, the number of constraints is also not fixed. It's growing like a dimension plus some constant, like in simplex. So n+1, n+2, n+3. Maybe it can be interesting. I don't know.
Okay, thank you.
Thank you. Any other questions or comments? Okay, if there are no, thank you very much once again. Thanks, Igor, once again for the very nice talk.
Thank you all.
Thank you very much.
Thank you very much.
Thank you very much. It's very interesting.